And if you do that, we derived an equation for the emergent velocity field, which is this very short line. And you can make it longer, like the last one. That's the quantum mechanical version of it. And in the middle line, we have an example for two slits, which is exactly identical to the Bohmian velocity field. So this, of course, is the guiding equation in different forms. But we think that ours looks quite short and elegant. And the price, of course, is that you have to use these relational intensities, which are non-local by themselves. So here are a few pictures from our simulations. As I said, these are, so to speak, classical, or rather super classical simulations on the computer. And we get practically the same trajectories as in Bohmian theory. There's interference with weak dispersion and a phase shift. You can add different average velocities, different spreadings, different probability densities, initial probability densities. Here is an n-slit situation with trajectories as we know them from Bohmian theory, and the Talbot effect. This one? Okay, it's on the net. You can download it there. Or, I mean, this is a playground for simulations. For example, you can have gradually diminishing weights and play around. And it's a very simple computer model. And you really can provide, all stationary problems and simulate them. So here's the Coudet analogy once more. As I said, we have a resonant interaction with a relevant environment. What is that? Well, for very idealized non-interacting particles, this environment would be the whole universe. And for any particle in an experimental setup, it would be defined by the boundary conditions of the apparatus. So if you start with the whole universe and some indefinite order, if you build up an experiment, or later if we switch something in that experiment, what we do is introduce or change boundary conditions which immediately affect the fields V and U. And that's what we call vacuum landscaping. So these two fields must be related to the probability density, which of course is how they are practically defined, U at least. And changing the conditions on these fields would then mean that you change the vacuum structure of the whole apparatus, and that would mean that you can provide some influence by this type of switching. What we call systemic non-locality is just this way of switching from one relevant environment into another. The essential thing is that the switching of the apparatus elements, particularly the changing of the boundary conditions, involving source and detector, entails no propagation, and also, of course, no superluminal propagation, and no signals. I just put it here, and then maybe in the discussion we can go into detail. The bouncer jumps in our model from one cosmological solution to another, so there is not some origin from which, when you switch, something is propagating and bringing that influence to some other place. So this violates Gisin's principle of continuity, but because he was considering also the option of V causality, that is that this influence in, for example, EPR type scenarios would propagate with velocities much larger than the speed of light, V being a tremendously big number, arguing that it would still follow a principle of continuity, of some kind of propagation. And he argued that, forgive me if I say something wrong, he argued that you can either have V causality with superluminal signaling or real physical non-locality. And of course, we argue for the latter part, that the non-locality is the reality that we are faced with. About the examples, I might talk later. Maybe we can finish now and start some discussion.
Yeah, fine. Okay.
Okay.
Right. Well done. Thanks for the order.